We literally pick up all the players you got and still beat you with them.
Hey, we gotta have a game on Christmas Day.
Christmas Day game?
Christmas Day game.
There's like a scoop break.
Okay. We're not doing the quick scene.
Okay. About the homework, some of the later problems were kind of stretch problems involving delta x. We'll deal with that later. That won't be on the quiz tomorrow, so I just want you guys to at least attempt it. And if you're confused, we'll come back and we'll revisit it when we need to. Okay. I want us to go through page 9 and 10, which is quiz review 1. Now, what you picked up is quiz review worksheet 2. I'm going to be using that as morning review tomorrow. So if you want to join for the help session tomorrow morning, which will be at 7:30, you can work through that with me. Or if you want to work through it on your own this afternoon, tonight, and see how you feel about all those topics. And if you can get through that worksheet on your own and you check your answers and you're good, there's really no reason for you to attend the help session because you should feel pretty confident with the material if you don't have any questions. Okay, so I encourage you guys to go through the review worksheet 2 on your own. But if you want to wait till tomorrow morning, that's fine as well. But either way, I think it's good for you to have a chance to try the problems on your own. Okay. Guys, there's one more minor topic that I want to go through that will be on your quiz, and that is squeeze theorem. So if you guys can turn to page 7 in your packets. Okay, squeeze theorem. This is page 7, bottom half of page 7. Okay, so let me read through the definition here. It says in the graph below, we have a lower and upper function that have the same limit value at x equals a. So I'll just try to draw the graph again since this is a little bit hard to see. So let's say I had let's say there's an upper function called h of x. So that here. And let's say I have a lower function called f of x. Say that's here. But okay, but then there's also the middle function. Okay, and what it says is that the middle function will have the same limit value if it is trapped between the two outer functions. Okay, so let's say we have 3 functions, and the functions all have this relationship where f is the lowest function, followed by g, followed by h. Okay. Now, let's say the upper and lower functions we have concrete information about, and we found that the limit as x approaches a is equal to some number, some limit. Right? We can tell that they both have the same limit. Okay. But let's say that we did not know much about g of x except for the fact that it's between f and h. Then your g function has no choice but to share the same limit value as your h and f because it's squeezed between the upper and lower functions. Okay. So that's really the big concept here. The big concept here is if I can show that my upper and my lower functions have the same limit, then I could conclude that the middle function must also share that same limit, even if we did not know, even if we were not able to find the limit explicitly for that middle function. Okay. So let me go through this example here. Okay. So let's say we have let h of x equals 1, let f of x equal x squared plus 1, and the relationship is established between the three functions, a lower, middle, and upper. So we have that to begin with. And it says find the limit as x approaches 0 of g of x. Okay, notice that we don't have anything about g of x, so we have to rely on the outer functions. But I'm going to go ahead and set everything up. I'm going to attach that limit statement to every function. I'm going to put it in this relationship that I have here. Now, we don't have anything about the middle function, but we do have information about the f and the h, the outer functions. I'm going to go ahead and make substitutions. I know f of x is x squared plus 1. I know h of x is 1. And because I have explicit functions that I can use, that I can evaluate on the outer regions, I'm going to take care of those. So what's the first thing we do with any limit problem? Let's plug in, right? So what's the limit of this smallest function here? 0 plus 1 is 1, right? So 1 is less than or equal to and what's the limit as x approaches 0 of 1? Also 1. Okay, so even though we don't know what the limit of the middle function is, if the outer function is if the outer functions are 1 and 1, then this middle function has no choice but to have a limit of what? 1 as well. Okay, so it gets squeezed between these two values, and if the outer functions are the same values, then the middle must also share that same value. So this is what squeeze theorem is, and you can expect a similar problem on your quiz. Okay. And you're always going to be given this relationship, and you're always going to be given information about the outer functions, and you're always trying to make a conclusion about the middle function. So if they're the same, then we know what the limit is. What if these are not the same? What if it was 1 and 3? Then we really we don't have a concrete idea of what that middle function is, right? So we would say by squeeze theorem, our limit is inconclusive, right? We know it's between 1 and 3, but we can't pinpoint the exact value. So either they match and we know the limit, or they don't match and we don't know the limit, at least not with more information.
So there won't be any like brackets or anything where it's like, or parentheses where it's like between some of them on 3.
No. Either you know the limits or you don't.
Okay.
Yeah, so it's only those two options. Any questions with that? The other thing that I did not include on your quiz review that will be on your quiz is something like this, where I give you a table of values and I fill in all the values and I'm going to ask you for the limit. So for instance here, if I say limit as x approaches 5 of f of x. So again, with limits, we always start on either end of our table and we move towards 5. As we move towards 5, what's happening to the y value? This side is getting closer towards what?
7.
And this side is getting closer towards, so therefore the limit is 7. Even though the order pair is living elsewhere, the graph is moving towards the same consistent value, so that's the limit, right? If I ask you for f of 5, that's something different. F of 5, we just look at the single point. But limit, we always look at how the graph is moving as we approach that target. So you see a problem like this on the quiz as well. Okay, so those are the big things that I want to make sure to go over. Why don't we go to page 9? And let's see if we can go through the top half. And then we can also practice with the problems below, bottom part of page 9. Okay, so go ahead and start with top half. Now remember, if a limit exists, I got to make sure. Well, if you want to test to see if the limit exists or not, make sure you plot points on either side of your target. Draw arrows and see if the arrows are headed towards the same y value. If it is, then limit exists. If it doesn't, the limit does not exist. Okay. After a minute or so, I'll put the answers up. Okay. For part 8, we know that infinity, if there's an asymptote, we know the limit doesn't exist. But if the arrows are headed in the same direction, we can still categorize it. So we say of infinity. Right, check your answers A through H. Hopefully you find these to be pretty easy, pretty straightforward, but let me know if you want me to go over any of these in detail. Everybody good with the top half? Let's go to number 2 below. Okay, so it's asking you to sketch a graph, or more, I'm going to say on the quiz, sketch a function, because we need to make sure that it passes the vertical line test, every part of it. I like to start off with the easiest things here. So start off with order pairs. Go ahead and plot them. -2, -1. Two, 3. Six, 7. So now I'm gonna move to finding limit. So for part A, the limit does exist. So my suggestion is when you see that the limit does exist, go ahead and plot a hole where that point is. And then extend the graph slightly on either side. You can choose to further extend it later on, or you can leave it like that. And you always want to put a hole there because at worst, there's another order pair that's going to fill in for that hole. But if you do this, you never have to worry about erasing and, oh, I realize that the point is defined elsewhere. So that's just the safest thing to do. Make sure you extend from both sides because the graph has to lead to that point from both sides, right? If the limit exists, I gotta be able to pick points on either side and head towards the same destination. Now, what you don't want to do is this. You don't want to put a hole there and put arrows on both sides. If you do that, that's basically going to fail the vertical line test because that line is going to extend on both sides and it's going to conflict with something else. So make sure you don't put arrows on both sides. Start with the short line segment, and if later on you want to connect it to another part of the graph, you can, or you can leave that alone. G of -5 is undefined, so look, I have a hole there, and I don't have to put anything else on -5, so I fulfilled that condition. Okay, the limit as x approaches -2 is negative infinity. We know that this must mean that there's a vertical asymptote. That negative infinity means that I have the same behavior on both sides of the asymptote. And make sure that your arrows are merging closer towards the asymptote. Make sure that they're not moving away from the asymptote. You want the arrows to head towards the asymptote. Now, questions that students have asked is, wait a second, so if there's a vertical asymptote, why is there a point that lives on that asymptote? And the reason why is because this is a piecewise function. We're stacking different functions on top of one another. So there's a function that has the branches and the asymptote, but then there's another function that's just defining the graph at that point. We can have that because it still passed the vertical line test. That point is not conflicting with any other part of that vertical line. So that's the only way that we can have this, right? There's no one function that will have an asymptote and a point defined, but if it's a piecewise function, then that's possible. F, limit exists, find the order pair, 2, 3. Put a hole there and extend the graph slightly on both sides. What do you notice here, 2, 3?
A point already exists.
Yeah, point already exists, so the hole that I was going to put here has been filled in, so the graph is going to be continuous at that point. Because I was going to put a hole there, but there's already a point living there, so I'm just going to extend the graph on both sides. And then for H, limit as x approaches 6 does not exist. So you have a couple of options. You can either make it a disconnected graph, which is perfectly fine. You can make it a vertical asymptote, which is also fine. You can make it an endpoint. And have nothing on the other side, which is fine. But what you don't want to do is you don't want to do this. You don't want to say, oh, at 6, I'll just make the point undefined and I do this, right? If I do that, then that's showing me that limit does exist, and that's not what we want, right? These are the options available to you, but you don't want to put a hole there and have the graph extending from both sides. So I made my graph, you can leave it like this, or just to make it a little cleaner here, you can attach some parts of it. But it's really up to you, right? I just want to walk around and see that you are, whatever decision that you're making, that you're fulfilling each of the conditions, but you're also not failing the vertical line test. Okay, so let me just check your graph real quick, make sure yours look good. Yep, that works. Yeah, you did it. However, there's an issue here, because it says that the limit exists at 2, 3. So I gotta have graph extend on this side, so I gotta have a slight extension on this side. I can't make it.
Because your solicitor has.
Sure. Yeah, it doesn't say anything about number 6, so you can make it a point there. Sure. I have to make this stop here, or you can let this. Yes.
Yeah. But if it goes conflict, it's that's 6, it's like the other side of 6, it goes to.
That makes it easy.
That's correct. Because that's twice the inside. This side is headed to make something. 7.
You come out.
This side is.
I know. That's the girls who know. It's exciting. Yes. No living is right. It's a great thing. It's just not.
Or, yeah, or you can do this, or you can stop there, go.
Yeah.
Oh, it's because I moved this.
Yeah.
The areas of each. So I need to do the bigger both sides, and both sides. No, yeah. Yeah. Well, there's a vertical aspect. Yeah, I can't have this. Exactly.
Yeah, so you kind of have to do. Yeah.
Second half, 7. And what does exist there?
Thank you.
That's number 4. Very specified is the first. Yeah. There's number 6, number 6. Number 6. Plug in that X. Yeah, that is.
Okay, I was just making sure that you left like the 5 in parentheses. 'Cause it looks weird, you know?
Zero or negative.
Yeah, so it's interesting.
Zero.
So do we have to put the other stuff?
Let's go to page 10. And let's practice through these problems, okay? All right, keep in mind, first things first, right? Insert your X value, see what you get. Show me that you're getting 0 over 0 before you jump into all those algebraic steps.
That's supposed to be 1.
That's a 1, yeah. Okay, as you guys try each problem, I will put the answers up. I really want to use this time where you can try these problems and I can help answer questions if you're stuck. Hmm? All right, so put the answers, the steps were 3 through 6 on the board, so check your answers once you've had a chance to try them. Step on any steps you need to. Okay, the limit notation. Okay, you're going to keep writing the limit notation until your expression no longer has any variables, which means that you've taken the step to start inserting, replacing your x's with numbers. So once your expression completely has all your variables been replaced, then that's when you know that your limit statement no longer needs to be written. But as long as your expression still has a variable in it, still has an x in it, that limit statement still needs to live in front of your expression. Again, don't assume anything. Show me that you're entering in that x value first, getting a 0 over 0, or a 3, or a 2 over 0. But this is the foundation that we need when we go into next week. Because there's more and more distractions coming up, and we wanna make sure that we have that first step locked down, so we don't try to do anything else. It's a good habit of doing that. Yeah, once you're here at the step, you're looking to cancel it out, right? You're trying to figure out what is that cause of zero to zero. That you figure it out. See that where zero plus each other. You cancel between you and just left with -1 over this one or x plus this one. Five parentheses, that's this one. Okay, does anybody still need to look at 3 or 4? Shift the page up a little bit. Guys, in this course, you're not going to need to rationalize the denominator. If this is a free response question, you'll leave radicals in the denominator. The only thing that I will say, though, is that on the AP exam, if on the multiple choice section, if your answer choice is rationalized, then you need to be able to match that with the correct answer choice. So that's the only thing. So if it's free response, you can leave the radical in the denominator. But you do need to know how to rationalize in case the answer choice is a rationalized form of the answer. Okay, careful here for number 5. Make sure that you are protecting that second term after you FOIL with a set of parentheses so that you don't forget about this negative being distributed through the parentheses and changing the sign of everything that comes after. I'll review 7 in terms of the factoring. I'll make sure that we're good with factoring, especially if there's GCF involved and the leading coefficients. Factoring review. This is after we've already tested out and made sure that there's a hole that is 0 over 0. So for number 7, if you're dealing with a trinomial factoring doesn't work unless the GCF is completely removed. So I got to take out the GCF. In this case, there's a 2 that's hiding there. Now that I have the GCF out, I can begin going through my factoring steps. So I know there's multiple ways that you can do factoring, but this is the way that easiest to explain here. There's A times C goes in that slot, C goes here, and then your A goes at the wings. Okay, A times C, 2 times 5 is 10. Negative 11 goes below, and then your A value goes. We go through our process, we ask ourselves what multiplies to be 10, adds it to be negative 11. Negative 1, negative 10, and negative 1. Double check it. Negative 10 times negative 1 is 10. That works. Negative 10 minus 1 is negative 11. Okay, so now we got to involve the 2 here because the leading coefficient adds to that additional step that we got to take. But we're getting closer towards our factor form. Okay, we always try to reduce the fraction if we can. Looks like this one we can. So we reduce that fraction and we get x minus 5. The second one here, though, however, I can't reduce that 1/2, but I got to deal with that denominator somehow. So I'm going to take that value and pull it in front of the x. There's a GCF of 2. I don't want to forget about it, so I need to make sure I include that 2 as part of my factored form. So that 2 is going to play a role in your final answer. Once you get your factored form, you should be able to find and see that there's a matching pair between numerator and denominator. Remove those, reevaluate, and find your way to your real number.
How did you get, 2x minus 1?
Because you're good with x minus 1/2.
Yeah.
So this is not quite factor form. I can't have a denominator in my factor form, so I got to pull that number in a different spot. I got to drag it in front of that x, so that's why I get that 2x. Okay. Any questions with 5 or 6? Nine and 10 are both common denominator problems with complex fractions. Check first that it is a hole in the graph, so always confirm before you move forward, but both giving us 0 over 0, so we move forward. Okay, let me know if you're stuck on any steps you want me to clarify anything that you see. Any questions? Okay, so tomorrow, morning, I'll have a help session going over this, worksheet 2 that you just picked up. But, if you can work through it tonight and feel confident, then you should feel good going into the quiz tomorrow. I did record, a help session from last year, so if you want to watch that recording and see if that will answer your question, if you chose to do it tonight, that's great. But tomorrow your quiz is going to be front and back. The only thing that's not on the quiz review is squeeze theorem and limit with table. But we can do a quick review of squeeze theorem tomorrow before you take the quiz if you like. No calculators. Okay. I'll send out a reminder this afternoon. All right, feel free to grab your phones. Yeah.
Can I take a picture of the?
Yeah, sure.
Thank you.
Oh, 9 and 10. Oh, here, just,
Oh,
yeah, to do that.
well, I think the conference is 8.
Oh, okay.
Actually, it's 9. I can-
Yeah.
They saved me last year. They saved me last year. I was 13. Oh, that's right there. Go on. It's the